in a second. Okay, sorry. Should I repeat or anyway? I just introducing my title anyway. So that's it. I must say a book sent Boston University people. So if you wanna know more detail about this project, you can get them coming here too. So first of all, usually my talk is there's like many terms in the title: family formula, mirror symmetry, cluster varieties, where two. So what we are going to do in the talk is we'll go over each items one by one. First, cluster variety. I will repeat. You will see my talk is we kind of go rough in the beginning, like, and then at the end we go more technical. We kind of repeating the same thing over and over. So right now, how do we see cluster variety? We see cluster variety as the usual definition are growing torus by some directional transformation like this, which is we have two tori, Caesar squared, and then we have this transition map. You can go or bidirectional map between the two, right? And then we glue the two torus together to obtain our cluster variety. But how do we understand this bidirectional map here? What does that mean? How are we going to see is actually this bidirectional map is obtained from follow-up of torus variety, which I I'm trying to hear myself. Is there any echo in the talk?
I think only this thing is unmuted, so you're only getting picked up once.
Okay, yeah. Good. And then what we start is with the simple like the simple model. We have the c squared, and the divisor is x equal to 0, and this is what we have. And then we go up at this point 0 minus 1. So this is x0, y equals to 0, the xy axis, and we go up at this point minus 1. We get something like this. And this is our go up. The details is the topic transform under this go up. And then what we can do is we look at this open piece of our go up. And then what we have is here, like we want to kind of go back to use our words to cover it. To map, whatever this is just a go up. So option 1.2, we define our go up this relation here. So the first map is just as we put the torus into just torus itself. So this is how the first map looks like. But then here for this and then here we mix the second divisor. So we have the second map, which is covering the curve here. So you can see here, if we look around, which is do this eta 2 square inverse eta 1. And then if we go back to do all the calculation of how to invert iota 2 and iota 1, then we go back and obtain this map. And you can see this one is exactly what we have as we advertise for this bidirectional map. So you can see here, if this is your first time seeing the definition of cluster variety, this ruling, this bidirectional map we have is actually coming from something very natural we have. So so the next one I want to introduce in my talk is scattering diagram. And in the beginning we said that cluster variety can be defined as growing algebraic tori, and this construction can be described by this scattering diagram. And then what is a scattering diagram? Which is something, a diagram on the lattice. So we start with a lattice, still lattice, and n out and n out. So a scattering diagram will be a collection of something we call balls with some more condition, finiteness, and consistent. We'll slightly talk more about consistency later. But then first of all, first question, what is wall? A wall is, as we might have immersion, the first piece is some codimension 1 code. But then with each wall, with this code, we associate a function on it. It's either a polynomial or power series. And here, let's go to an example. not now. Here, the wall is of codimension 1, so it contains in some hyperplane. And then how we have this function is a function in a variable that lies on this hyperplane. So this is roughly how our walls looks like. So as you can see, this is our example of scattering diagram. We have 3 walls. And you can see here, it's like we have way as well. So the wall is just containing in the hyperplane, but it might not be the entire hyperplane. And you can see here for this wall, we have this point -1, 0. So this wall function is a polynomial 1 plus a1 inverse. In general, it might be in series as well, but only in this example that it is a polynomial. Here, look that I'm going to use topic notation here. So set -1, 0 just means a1 minus 1. Just a notation. And the variable I choose here is a instead of usually we do x. So what we do is we have scattering diagram consists of wall. So what we want to do, if in Cheung time and I was in Mexico, I'll be like, I'm doing wall crossing. So and that's what I usually tell people, but I'm not in Mexico now. So we want to cross a wall. So what do you mean by crossing the wall is like this? Literally, I have a path crossing the wall. But what does that mean? It just means that I define an automorphism on the polynomial or monomial like this. So a wall crossing is I map a monomial set over M with I just fix a cell, but then I multiply this wall function up to some inner product and sign. And usually it's better to illustrate how we do that in an example. So we pass this wall. So let's start with this monomial set -1, 0, set -1, 0 here. And then I have this wall function here, so I keep it here. And then I have this inner product. How do I do it? Is I fix this M, so it's -1, 0 here. And then here, this n0 is I choose the normal vector opposite to how I cross my wall. So it's again -1, 0. So you can see I got a 1 here, which when we spell it out, it's something like this. Here I know it's Northeastern, and I'm not sure you are, but I know like Gordana, they are working as cluster algebra, and if you are cluster algebra people, not that a geometry people, you can see immediately that this is the custom notation in the family series key definition. But if you are not, you can see this map, this bidirectional map was just the Google map we were just talking about. So now we slightly talk about consistency. Consistency just means that in this picture I cross one wall, but then I can look around my wall like that over the origin. So roughly speaking, a consistent scattering diagram is a diagram such that when we perform wall crossing by looking around the scattering diagram, we always get identity. Like this is a consistent one, but an example we are going to see is we can start with something like this. This is a scattering diagram as well, but not consistent. And the construction is we need to add this extra way here to turn the scattering diagram to be a consistent scattering diagram. So, like we say, we define scattering diagram to talk about the doing of clusters variety. So the way we do is we associate each maximal cone of the diagram with the torus. In this case, will be a 2-dimensional torus. And then how we do is we have this wall crossing, and like we just suggest in the calculation, the wall function are actually just the doing function that we have. So the construction is simply like here, we have 5 torus, and we do the torus here by the wall function we have. And then when we do together, we got the cluster ID. In this example, we are going to talk about the other type of cluster ID. So let's say here, this is the A cluster variety of type A2. So this is how you can see sketching diagram give us tells us the cluster variety, the Green construction. So what else can we do? And we are going to see what one of the main purpose to construct sketching diagram is to construct function. So the one example we are going to repeat in our mind is torus, like here two-dimensional torus. The function are just Laurent polynomial that is sum of monomial, linear combination of monomial, and each monomial are indexed by two integers. So you can see here we have a set two lattice to talk about the function of the monomial. To talk about the monomial on the torus, that we can talk about the function of it. So this is what we have in mind. So what we have now is on the lattice point. Here we have some scaling, but let us now just take this M sub as the lattice point. On each lattice point, we associate the function. How do we define it? Let's go picture again. Phasor function, the full definition is very combinatorial, but quickly, roughly speaking, it's defined by something we call open line. With how does the open line looks like? Which we turn this point to the initial slope of an open line, and we fix one more point, end point of the open line. So you can see in the picture we have, this is what we have in our mind. Our initial slope is -1, 0. That gave me initial slope -1, 0. And you can see I emphasize we do opposite direction, that we go in 1, 0 direction. So we fix our endpoint Q here, and that is my first open line. And then the open line, as the name suggests, it breaks. And so it breaks over a wall. And you can see here, similar to the definition of wall, is not only we have the geometric object, we always have some monomial associated to each line here, each piecewise piece of linearity here. So you can say basically this monomial agree with the direction of the line, but when it bends, this bending follow what we have for the wall crossing. Like in our calculation before, we have this, it is -1, 0, 1 plus set 0, 1. And so here, I got a set -1, 1 here. And you can see this give me this bending here. So,
sorry, quick question. Can you remind me what this capital M is?
M is just a lattice point. So
I see.
M will be just AB. Yeah.
Okay.
No, it's a good question because you're going to see it's very rotationally heavy for this this aspect of math. So anyway, great. Any more questions? Okay, also slowly move on. Please just pause me anytime you like. So this is the two open line you have. And we can try all the combinatorics. This is the only possible open line we can have with this given initial slope and this given fixed point Q. So this is our Phasor function. We define as summing up all the final monomial we can obtain from this version of open line. So you can see it's -1, 0, and -1, 1. And you can see here again, if you're a cluster people, you can see this is nothing but just our calculation we had before. So, because I know there's so many cluster algebra people here. So in the cluster algebra term, you can see that is how we can have the cluster monomial. But in general, we need to have open line because we might pass through infinitely many walls. So, like with some infinite case. So here, so in the what we call cluster context, like Phasor function can be defined by open line or wall crossing, but if you get outside, then then this is how we define theta function. So we have theta function. So it is a regular function, but then the next property that we are looking for is the algebra structure. It's still going back to what we have for this two-dimensional tone line. It's not only that we have the ring of regular, the function are generated by the monomial, but also that we can multiply the monomial each other, or we can multiply two polynomials and express it in terms of summand of other monomial. So this is what we are looking for. We look for the vector space generated by theta function have some algebra structure. So here is it. This is what Gauss-Hopkin cube show, which is when we multiply two theta function, it can be expressed as linear combination of other theta functions. So you can see here, it carries some algebraic structure. And you can see I'm slightly being careful here, because the thing is, this linear combination might or might not be finite. But you can see here what we are looking for is in our mind, we are thinking of finite, like a vector space thing. So so this is what is called a Floer and Boucher conjecture, which is if this collection of theta function does give the ring of regular function of cluster variety, which is not true in general, this is true under some condition. So this is what we have. We will consider this called middle cluster algebra, which is algebra that when generated by the theta function of polynomial. So you can see I do this bracket polynomial here, which is when theta function are finite, and then what Gauss-Hopkin cube show is this is an algebra, but it's not in general that this is the ring of regular function of cluster algebra. But you can see here what we do have is we have scattering diagram will give us theta function that are regular function on cluster variety, and the collection of all those theta functions are very likely to be the ring of regular function of the cluster variety. But in most cases that we can, even though I'm very conscious here, but I must say in most cases of concern, they kind of equal. So that is the game goal. In the top title suggests we are not paying just algebra, we work with mirror symmetry as well. So the mirror symmetry or mirror construction in our mind for the first part of the talk is this Gauss-Hopkin cube mirror construction, which we start with a smooth convex projective survey, and we choose a canonical divisor, which you are going to see the example we have will be Cheung of curve, -1 curve. So how their construction is, they give this pair, and then they construct a topicalization of it, that they define an affine manifold with singularity, and this sigma is a cone decomposition. Actually, it's coming from this divisor. Actually, we're going to have example very soon. So the example we have in this line is in our mind CP5 and Cheung of 5 -1 curve. And then when we do the topicalization of it, we copying this cone here. This is like slightly, you can see not the same as cluster case. In terms of this B is not R2, but it's an affine manifold. What do I mean here? You can see I have this gray region here, which this line actually, that's this affine structure that put this line with this line, the positive x-axis. So you can see it's not fully R2 almost, but there's like some affine structure on R2. So this is the topicalization we have. And you can see it's almost like our scattering diagram already. So what we do is we want to define canonical scattering diagram on this affine manifold, which is the same, but it is dimension 2. So the walls are just way coming from the origin, and then we have 4 functions here. But you can see here, I used the term canonical scaling diagram, but not cluster scaling diagram. The reason we are going to say is the coefficients here are not coming from cluster theory, but the coefficient coming from some curve counting invariant. So that is how the construction goes. So in this example, this is our canonical scaling diagram. So the construction they have, the rest is almost like what we have done. So like I said, this time you can see I'm going to repeat the same thing over and over again. What I'm going to do is we still have the chambers, and then we glue the chambers by this wall function to obtain our open seam. And on there, we similarly, okay, I have the picture here. And then we similarly define phasor function the same way on the affine manifold. And then what they do is they show that in that case, the collection of phasor functions does give an algebra. And then the proposed mirror, the GHK proposed mirror, will be the step of this algebra. Let me see. Okay, phasor Q. Something like that. So this is the construction. So you can see this is the idea. So it's like almost exactly like the cluster thing. And one thing maybe let me point out is even though this mirror, like this scaling diagram is on an affine manifold, but you can identify quote-unquote, okay, not everyone is seeing the quote-unquote, identify it with like cluster variety in the sense of, you can see in my next slide, the idea behind is we have the Lagrangian vibration. So in the vibration, you are thinking the singularity is at the origin or at infinity. You can imagine pulling this singularity to infinity, then you will obtain the cluster scaling diagram we have said. And actually, that is one part of the two-finger GPRT construction. So with usually, what we do is we translate this algebraic setting to the family 4 setting. So what we do is we do for rational elliptic surface of 3 types that we are going to see. Like this is a Gross-Hopkin Q, Gross-Hopkin Q mirror construction. We have scaling diagram, like I said, like this is the days of target generation. We have waves, and we have functions, phasor functions, like wall functions, left function, wall forcing transformation. And then what we do is we look at Fukuyama's construction, and then we identify all these things as holomorphic disks, like the function, like origin in the GHK are A1 curve, but then we see them as Maslov index 0 counting. And then the wall forcing, that is actually the Q part, which is in the family 4, they have the Maria Canton space. And then we identify, actually, this is kind of a where two things, because the Maria Canton space in this case are actually analytic tori, but not true in general dimension. But then what we can do is we can then use the wall forcing to give the isomorphism between the Maria Canton space. So this is what we identify. This is what we do. You can see we will translate the thing in the Gross-Hopkin Q mirror. We do the torus, which is like Laurent polynomial into variables. We turn it into Tate algebra in analytic geometry sense, and then we have torus, 2-dimensional torus. We turn it, in general, will be rational domain, but in our example, they are mostly just analytic torus. And then the gluing, we are doing the same gluing, but now here we are in the analytic geometry sense. But we can pass from the algebraic to the analytic geometry sense because you can see the wall function, like this A2 example, or in our example that we're going to say, is very simple, they're algebraic. So Gaga tells we can lift it up. So this is what I have a fusioning, which is we explicitly construct the mirror, family 4 mirror for this rational elliptic surface of type 2, 3, and 4. And they are exactly, here is the cluster variety of type A2, B2, and G2. Those are the 3 finite cases of rank 2. So we explicitly construct this mirror out of this setting. Like this theorem, I know if you're the first time hearing it, it might not sound very exciting, but I must say here this family 4 mirror was laid out by Fukaya, and then later on Apostle showed that for family 4 mirror function will deduce homological mirror symmetry, and then to lay out the construction, and then we have Cheung gave the construction for toric case. But this is kind of the very first example for non-toric setting. Like the theory was there, is there, but like, is there any example? It's unclear. But then you can see the two things nicely match together, and then we give the example. But you can see this is only 3 examples, so we can ask, can we do more than that?
Just a basic question. So if you're talking about, say, a type A, B, C, D, or whatever cluster variety, then one like with scattering diagram coming from the file chamber.
Almost. There's like some Lie theory involved. Like that's the algebra. Like for the formal series key when they define it, they like I keep on emphasizing that a finite type and infinite type. And formal series key show that the finite type has bijection with the thinking type. And then what they further show is the custom variable are in bijection with the all, I forgot the term, non-negative root. Right. Because like A2 is it's the root system, but then my sketching diagram is this. Like we don't have this.
Okay.
I forget, like no. So that's like one term. You see what I mean? But you can, that's not the almost. But yeah, you can see like the prettiness. They are actually all lines up together. When I'm using this A, B, C, G, yes, they are the same thing. Yeah, but from a very algebraic point of view. Okay, good. Maybe I should pause before I go to the next part. Is that okay for this first part? Okay, good. You can see in the first part of this talk, that's like managing a really weak. Like I said, the canonical sketching diagrams come from some curve counting, right? I'm still going to be weak, but slightly more precise. The curve, then we have a bunch of curves, but the first curve we come into mind is tropical curve. Tropical curve are piecewise linear curve, which satisfies some balancing conditions. So it is something like this, and each vertex, we look at the direction, like the edges that join that vertex, and then we can see summing up this 3 direction goes to 0. Negative direction. There might be some weighting as well, but in this example, there's no weighting. And one more example of tropical curve would be something like this. So those are our tropical curves, some piecewise linear graph. So we can see how that go back to sketching diagram. A tropical curve. I should have one more slide, right? But you can see here already this tropical curve is lying secretly inside a sketching diagram, and this is not something special in particular. This is in general for this consistent sketching diagram we have that is looking around this identity. That condition actually are telling us that this 4 function here in the construction are actually corresponding to this tropical curve. Like in this example, it's like this one. Because you remember we start with something like this, and then I say we add this wall here, and this is how we got this picture. And then this one here is telling us, okay, you talk to me if you want more technical, because you know the definition will be like for a collection of direction, a collection of waves, and then we define the tropical curve with certain condition, and then the count of those tropical curve with some scalar will be this ck. But you can see in this picture, this is counting this tropical curve here. So what we honking and but then why do we care this tropical curve? Like if you're not a tropical geometry people, what we honking and Nishino Siebert generalizing the constraints result is this tropical curve counting is just the homomorphic curve counting. And then what we've said that even at Hanselholm and me, what we do is we look at this tropical homomorphic correspondence. We turn the counting of this Maslov index series to tropical curve counting. If you remember in the table I have with Lucian, with the 3 finite example we have, we turn the wall into Maslov index zero counting. So you can see what we are doing here is to kind of generalizing the way we were doing, but not exactly like the construction is not exactly the same, but you can imagine it's kind of generalizing it. So the rough story of how this looks like, skipping all the synthetic geometry and anything, which is we start with a bunch of, again, we are in the way to surface example. So we look at a collection of primitive vectors in set 2, and then we construct the scattering diagram we have in mind. You can see the initial scattering diagram we have in mind is we look at the line with that direction, and then we look at we associate the wall function in this way. And the construction is always like this. When 2 walls meet, we add 1 more wall. Like here, if I have 3 here, like this is how we have, like for the initial wall, whenever it intersects, we'll keep on iterating and add more ways associated into it. And so that's like we consider the consistent scattering diagram containing the initial one, and my laptop is unhappy now. Consistency. So, but still, like I'm just talking about scattering diagram. But what surface that we are counting curve on, right? So this is how we have. Here we have a bunch of and many primitive vector. We look at the surface, the toric surface defined by this fan, which is like this. And then here we have a fan. Let us assume complete. It doesn't really matter if it's complete or not, but let us assume this is complete. And then we look at this toric surface, and then to each way here that corresponds to divisor. So we have the divisor, and then what we do is can see the same thing. It's like we'll repeat the same thing in the beginning. We want to go up at points on the divisor, and then we look at this TV tutor, which is the bulb of the variety coming from the fan at the point on the divisor. And then this scattering diagram we construct the wall function to give the counting of this is gross source and the like we'll give they will give both the tropical curve count and also the counting of genus 0 curve with more conditions. Like when we go up, we have the exceptional divisor, so the intersect those exceptional divisor and tangent to the outgoing direction.
Just so the divisor is code section 1, so when you roll off
no, at some point, you're right.
at specific points in the divisor.
In here, we don't really care. It's just a point, but in the toric variety, we're going to see it's very specific. Yeah.
It's like a torus fixed point in the divisor, or just
It's just like it just like some point, like in okay, let's say like in here it doesn't. I don't think it's like just some point. it's okay. But then in the custom, we'll be very specific about what formula we are going. So I hope, okay, it's not that precise, but slightly more precise for what we work with Floer, even Horn and Mean is what we do is we parallelly, not parallelly, but we have constructed a Lagrangian foundation, and then we define the Lagrangian force scattering diagram, and then here the wall are consisting of Lagrangian fiber that bound myself in the zero disk. And then what we show is, and like I suggest, we use this tropical holomorphic correspondence that we know that tropical curve can equals to this like holomorphic curve terms. And then you can see here we can identify this four theory scattering diagram with the GPS scattering diagram. So this is what we have to do with selector. But then as the concern of this topic is, well, customizability. Let's go back to customizability. So here is slightly more technical formal definition of customizability. Customizability are defined by a collection of data. We call fixed data and SIP data. Fixed data has many things. What from the lattice end, we have a skew symmetric form, some integer PI. Again, if you are cluster algebra people, when formula series keys define cluster algebra, they have this skew symmetrizable but not symmetric matrix. And this DI is the integer that turns this skew symmetric form into skew symmetrizable matrix. And we have SIP, which is the basis of the lattice n. And then here with the lattice n, we have the dual lattice. So we have a basis, we have dual basis. And then, as we said, in our mind, we should be thinking about this skew symmetrizable matrix. So we'll look at a scale lattice with basis coming from scaling by those DI. So like we said again, customer variety of moving of torus. So this is the construction with one seed will associate. We are associating a torus to it. So this is our exact and exact. And the seed will mutate following with some mutation process. And then what we are going to associate is we'll relate a seed torus. And here, let me say a seed. I will mutate it, which is another basis. And then here is with a seed, I will have, like in the A cases, one torus, here is the other one. And then we define this bidirectional map between them. And then this bidirectional map is just the bidirectional map we set in the beginning. But formally speaking, the X mutation is something like this, and the A mutation is like this. And this is how we distinguish those two types of cluster algebra, cluster variety, by the difference between their mutation map. So I think that it's going to be notationally heavy. So let's just remember something right now. This CI here, we mutate 1 plus EK, and mutate at A is 1 plus set VK. Oh, I didn't define VK. Okay, VK here is just I have this skew symmetric form, which is I put this EK there. This kind of dual of our EK, something like that. And with the inner product like this. And then what I want to further introduce is we have Lagrangian dual cluster variety, which can be emergent as the transpose of the original cluster algebra. Actually, it's literally the transpose. I have just uploaded this paper on generalized cluster. In the last session, I explicitly compute why lambdas do are negative transpose of the original one. But if we forget that, how we do now is we we define a fixed data for landing field, which we look at the integer as d. Here is the LCM of the original di divided by d. And then here we look at this lattice, which is the scaling of the original one by the d. And then you can see here I have this symmetric form, it's dividing this LCM. And let's understand everything by example. So here is again dimension 2, skew symmetric form 0 minus 1, 1, 0. The D1 is K, D2 is L, K and L are co-prime. And then on the A side, the mutation, if we dictate everything else, the directional that we have are things like this. And on the other hand, we look at the landing field X, and then the directional map are like this. So you can see here a few things to observe, which is here is A1 to the L, A2 to the L. But then here I kind of pull out my bracket. And the second thing you can see is I kind of changing my exponent. And this is kind of what one can imagine about what mirror symmetry is. Like what I'm going to propose is the A cluster variety are mirror to landing field of X, and X are mirror to landing field of A. It is not that pretty in general, but like this might be the picture one can have in mind. We pull the exponent out and we flip the exponent. So it's like some duality between the variety. So this is what we have in mind. And then like the next thing is we want to talk about how we blow up. So we look at the fan. That is the fan for the A and X cluster variety. And then you can see it's like the same picture. We have the total variety. We have DI the divisor corresponding to the one-dimensional way. And like I said, the bullet point is very precise here, which is you can see we look at the zero locus of our mutation map. So in the A case, if we go something up like 1 plus A1 squared, we just look at the zero. Because like this will be intersecting at A2. So A2 is 0. So you can see that's why in my example, in the beginning, I do the point minus 1, 0, which is, you can see, is something like this. 0 minus 1 in my example. But it's like it's very precise. In the cluster world, we just look at the 0 coming from our mutation map in both A and X case, and we go up at, and it's in particular easy in way too, because fundamental theorem of algebra over algebraical constraint, we just have points. No, actually, this is one thing we use to conclude at the end. It's like funny, but that is like at the end how we conclude the landing field part. And then we blow it up. So this is formally we have the TV tutor associated to the both of the variety A and X one coming from the A and X fan. And then we look at the open piece of it. The one thing here, because even though we define cluster variety, but the idea in mind is still multivariate from cluster algebra. So actually cluster variety is something defined only up to codimension 2, because the algebra will kind of be the same. So we nail down to our rank 2 case. What do we mean by rank 2, which is the skew symmetric form in fixed data of rank 2. So you might have something like this. This is rank 1 actually. Let me add one more. Like it's kind of a 3-dimensional thing, but we'll say this is rank 2 because for rank of this matrix is 2. So what we are going to do is we look at the kernel of this matrix. And then the kernel, because it's embedding to the lattice, that will give a torus action to our bigger torus that will induce this TK sub action actually first on the each torus, but then the torus action commute with the mutation. So that is, it gives the torus action to the cluster varieties. And then what we want to do is we look at this quotient of A variety by this TK submap, and we want to just do everything very parallel analogously, and describe the torus model of it. So this is the part that is it. So you can see what we are going to do is we have the lattice, we quotient everything with K. So it's like long, but the idea is very nice. We just quotient everything with K. And then we look at the fan under this quotient notion. Originally, the A fan is just coming from our VI, but then how I have this VI bar, it's just VI, it's like VI under the projection map. It's like this N goes to MK, and then VI map to VI bar. And that's it, just quotient everything down to this one to lattice. And then what we do is we just repeat the same procedure. We have a fan, and we have this variety. We look at the ball of the variety of the zero locus forming possible from the quotient. So this is what it is. And then, so this is the torus variety we have. We look at the ball of torus variety, which is isomorphic. Taking out the boundary divisor, that will be isomorphic to this quotient up to codimension 2. So we have this torus model. So the next thing we can see the title is going to say is we want to look for the scattering diagram associating to this torus, this ball of torus variety. So this is our fan. And what does the GPS construction tell us? We start with n many primitive vector, and we look at the scattering diagram with just line coming from those vectors and associate the wall function. Here we have the DI associate the direction to it and give us the function, right? And you can see here I have index VI bar here because when we are looking at the zero locus, okay, this is really fundamental theorem of algebra. Zero locus of the bidirectional map, we have n distinct root coming from the degree of the polynomial. So we have index VI bar many column going up. So that's why we have that many wall overlapping each other. And you can see here one thing we have said in the beginning that even though it's notationally heavy, one must set something VI is something escaping diagram. And I put the DI here that gives me the magnitude. It's something look like this, not exactly, right? Because we are looking at quotient. So what does that mean here is while we have K embedding, K sub embedding to N sub gives us a torus action of the A variety, we can say magnitude of K counting magnitude of N that will induce a vibration of the X6 torus. And this modism commute with the custom mutation that in general we can see the X family as a family over this T then still K star on campus. So what we have for this scattering diagram is actually we look at the fiber, I cannot write again, the fiber at the identity of this vibration, that space that we are looking at, it doesn't work. And then this is actually the scattering diagram of this thing. So sorry, maybe I finished a bit early, but this is the mirror symmetry statement we can have. Luckily, the quotient of the A cluster right here mirrors to the Lenin still X family at fiber at the identity cluster variety. Here, roughly, as I emphasized, because what we have is more precisely what we obtain is we have this random stable XE scattering diagram, and if cases are good, that the algebra generated by the theta function are finally generated, then we can take the algebra out of it, and then the spec of that algebra will be the random stable X fiber at identity. Okay, you know what I mean. Space, but we still have a mirror statement because we just have the scattering diagram at the end, and you can see all the construction before very algebraic, but we can conclude this mirror is also a family for mirror in terms like we said early on that with the even Hong and Lin, we construct this Lagrangian for scattering diagram is the same as the Gauss-Panner series scattering diagram, so we have all the invariant match. But that construction is only for monomorphic board, which is the case that when we do the closure, the EI are still primitive. But in that case, we can say we do not only algebraic mirror, it is also a Lagrangian form mirror as well. And yes, I'm going to finish early. But thank you very much for inviting me again and being here for this talk.
Any questions from the Zoom audience? Questions from the in-person audience?
Just maybe why is there this nomenclature of Blankland School for class? So how does that square with the sort of traditional things that one uses Blankland School for?
Yes. Here my setting very restrict. Here my I have restrict my cluster variety to the setup which is called without Folsom variable. And there's like a type of cluster algebra that have with Folsom variable. And there are a bunch of examples there, which is Bosmanian homogeneous space fat variety. And what is supposed is the fat variety coming from G mod P, the semi simple one, mirror to the adjoint one. And there you can see the transpose of the Lennon still coming. So I believe that is kind of the motivation why we care about the Lennon still. So, and actually in this mirror symmetry, in this scattering diagram, you can see that too. Because you can see one thing I kind of sloppy is I set this D lines in M sub, which is some scaling, right? And actually that corresponds to the topicalization of the Lennon field of X trop. So like there, when you do topicalization of the Lennon field variety, the pawn actually give you the idea is the A variety. So I believe that is also why, okay, the first variety one, I guess, is kind of more empirical reason, but this topicalization picture is what I believe what for an contract might have in mind. So you can see things really go in a duality way. Yeah. I don't know.
There's no more questions. Let's thank Mandy again.